Welcome back. So for this next part, I want to first provide a little bit of motivation and some intuition for what's going on. So let's go back to where we had a symmetric positive definite matrix. Then we know that A can be broken down like so, where V is the matrix of eigenvectors and lambda is a diagonal matrix of the eigenvalues. However, and we called this spectral decomposition, or sometimes we applied that term to the sum of outer products. But regardless, we were able to break this down. We also know, because A is a matrix of any kind, that we have this relationship. So what is the relationship between sigma and V in our second system and U in the SVD? Well, for this case, for its positive symmetric, positive definite symmetric matrix, these can be the same. So when I say can be the same, it turns out there are some subtleties where we could use rotations to change things around a bit, but for now we won't, and we'll just show this. So an SVD could be V sigma V transpose. It's the same as before. So why do we care about this? Well, we care about this because we can define our maximum reconstruction error as we did before. In fact, rather than just rewrite it, I'll pop back to that slide. Here, where we had the reconstruction error looks almost identical to what we found when we were looking at our when we were looking at the SVD based reconstruction error. So let's copy that. We'll go back. Here we had our reconstruction error shown in red. What's the difference? The only difference is we're using the singular values instead of the eigenvalues. But in the case of a positive definite symmetric matrix, the singular values and eigenvalues are going to be the same. Well, where does this get us? The same, and let's just paste that beautiful little diagram there. This could also be sigma squared of 1 and sigma squared of n. Would have worked in the same place. So when we did singular value decomposition, however, we could also deal with a case where we did not have a positive definite matrix, In fact, if we had a positive semi-definite matrix where we had at least one eigenvalue equal to 0, then that would have been the smallest value. Let's just say, for the sake of argument, that the smallest eigenvalue was 0. Using the spectral decomposition based on eigenvalues and inverting, which we couldn't, we would find that the error would be multiplied by 1 over 0 and it would blow up. Okay, well that's not the case, but let's look at something really close to that. Let's kind of follow this down on the limits. What happens as lambda n approaches 0 from the positive side? So it's not 0, but it's approaching 0. Well, the reconstruction error blows up. That's what happens. Technically, the matrix is still invertible, but it blows up. So, as it actually hit 0, what would happen is that error blows up. When lambda n equals 0, we can no longer use a inverse. I must use the pseudo-inverse of A. So the pseudo-inverse is going to essentially then the error is bounded by 1 over lambda n minus 1 squared. Okay, did you see what happened there? When the when the matrix is still invertible, we already know that the pseudo-inverse and the inverse are identical. And in that case, the error just blows up. However, once the matrix is no longer invertible, lambda n is now equal to 0, the inverse doesn't exist. It got perilously close to having an infinite condition number, and then the singular value decomposition takes over, and the singular value decomposition just simply ignores that 0 eigenvalue. It just gets rid of it, and suddenly the error is now bounded by the next one. So, singular value decomposition is essentially inverting the matrix in every dimension it can, and in the one that it can't, it simply ignores it and does nothing with it. Well, this should provide some nice little inspiration. Let's take a look at what we could do with singular value decomposition and pseudo-inverses to make things even a little bit better behave. So we have A is equal to some matrix U, and let me introduce one other thing first. It will maybe help with this. Let's do this. If we define our eigenvalue a little bit differently, similar to the proof that we ran the other day. Like this, we can discuss what's going on. First, some textbooks define SVD this way. I find it easier not to, because we want to talk about sigma inverse, which is difficult to do, and so they have to, textbooks that define the SVD in this manner find that they have a harder time notationally describing some of the things that we do. So when we normally define it, we're defining our pseudo-inverse in terms of these quantities. So if we were to plot these values, we always have them sorted. So there's R, and sigma R is always positive. I'm sorry, I put the squareds there and I didn't mean to. Here we go. We might have, for R equals 1, 2, 3, up to capital R. Using this definition that we see in other books, which is the same except that it includes those zero parts, the singular values are always going to be sorted by size. And then thereafter, they're all zero. Now this one right there, that's our troublemaker. This is the one that amplifies the reconstruction error. Well, what if we just said, well, yeah, that's pretty close to zero. What if we just eliminated that one and called it zero? If the next one is much larger, then we've gotten rid of our major source of reconstruction error, but at what cost? The cost is we've introduced new error in our pseudo-inverse. And so we have these trade-offs that we might consider. And today we're going to look at what happens if we eliminate that smallest value So let's go through and first get a little bit of notation here. Y equals ax plus e as before. A is, of course, now we're going to look at a is m by n, no longer the square version we had before. And so we're back to away from our little discussion that gave us kind of the motivation, but back to our actual case where we don't have an inverse that we can talk about. Everything has to be back in terms of our singular value decomposition. So, and we're using our traditional SVD definition, not the augmented one. So we have sigma is R by R. Okay, we can write A as a sum of outer products so this is a as a sum of rank 1 matrices, and just to keep everything clear, we have UR is m-dimensional, and it's from our matrix U, and VR is n-dimensional from matrix V, and A dagger can then be written in a like manner. It's 1 over sigma R times VR UR transpose. So you can see we've swapped the order from our expression for A. Okay, we're getting our terminology down. Now let's say we have X least squares defined as we did before is A dagger times Y, and that's equal then to, using our sum of outer products form, Y comma UR times VR. And we've already well, actually let's express this out just a little bit more. It's 1 over sigma R, and Y is AX plus E, so we can write it this way. We have AX with UR times VR plus, now the E part, E with UR and VR, like so. So here, as we saw before, a small sigma R translates to large 1 over sigma R, which is equal to large error term. So what happens over here? Well, for here, for small sigma R, AX correspondingly is small. Actually, it's technically it's AX projected onto UR is small. So they cancel out, and we don't have a problem there. So now we can finally look at what happens when we get rid of the offending smallest sigma R.